Evaporation and condensation, section 12.4. So evaporation, another word for that is vaporization, is the name of the physical change from the liquid state to the gas state. So the rate of vaporization, how fast something evaporates, is going to depend on several factors. It's going to depend on the surface area. If the surface area is greater, then the water will evaporate, the liquid will evaporate faster. If the temperature is higher, it will evaporate faster. And if the intermolecular forces, the forces holding it together as a liquid, are weaker, it will evaporate faster. So liquids that evaporate easily, we say that they are volatile. And we sometimes use that word in reference to people's tempers or their personalities. You know, he's very volatile. You just don't know when he's, going to go off in a rage or something. Easily set off. So a volatile liquid evaporates easily. Something that doesn't is considered non-volatile. So let's look at evaporation. So we've got molecules on the surface of the water. Those are held less tightly than the ones in the interior because they're only held from the sides and the bottom. They're not held on the top. And so they're held less tightly, and it's easier for those to escape. Remember, temperature is related to the thermal energy, the kinetic energy of the molecules. It's an average, though. So some particles are moving faster than others. They're not all moving the same speed. So if you have an energetic molecule, one that's above average at the surface, it may have enough kinetic energy to escape from those intermolecular forces that are holding it in the liquid. It can escape and it will go off into the gas state and it will just travel until it hits something. In an open container like this, they'll just fly away. There are also water molecules in the air, and if they come down and come in contact with the liquid water, if they crash into the water, then they tend to get trapped. So the most energetic particles will break away, and this is called evaporation. So at a given temperature, only some of the atoms will have enough to evaporate, a small fraction. So this graph shows us, it's graphing fraction of molecules that have a particular energy. So kinetic energy going this way. And so at some temperature, let's look at the blue one first. At some lower temperature, most of the molecules have about this kinetic energy. There are a few that have a very high kinetic energy. And so we get this curve representing the number or the fraction of molecules that have those particular energies. And so most of them are in this range. In this graph, this red dotted line is showing us the minimum kinetic energy necessary to escape. You have to have this much kinetic energy to be able to break free from those intermolecular forces that are holding you in the liquid. Well, at this lower temperature, only these molecules up here have enough energy to escape. If we raise the temperature, this red line, now we've increased the average kinetic energy, and now we have more molecules that have enough energy to escape. And so the liquid will evaporate faster. And you've probably experienced that in real life, that cold water evaporates more slowly than warm water does. And, in the dryer, why does the dryer heat the clothes? To make the water evaporate faster so they dry faster. The hotter the temperature, the faster they dry. But, sometimes it can damage your clothing if you go too high, right? Because if you put them in a fire, they'll dry quickly too, but they'll burn up. So at higher temperature, more molecules have enough energy to escape. So evaporation is faster at higher temperatures. Condensation. Oh, where is this going? Okay, I just want to talk about these two other factors. increasing surface area. Why would increasing the surface area cause evaporation to go faster?
Because it's easier for them to escape on the surface, so increasing
Right.
surface area makes more of them on the surface?
Yes, a larger surface area, they can only escape from the surface. They can't escape from the middle, so they can only escape from the surface. So if you have more surface, they'll evaporate faster. So, you know, if you had a glass of water and you took another glass of water, same amount of water, same temperature, and poured it on the table or on the floor so it's spread out, the one that's all spread out with larger surface area will evaporate faster. So we talked about increasing temperature, decreasing strength of intermolecular forces. So let's look at that graph again. So this was the minimum kinetic energy needed to escape. If the intermolecular forces are weaker, that line gets moved over here. It would get moved over. Let's see, what color do I have? Well, let's go with red. So, don't do that. So weaker intermolecular forces moves the minimum required energy to escape. It's easier to get out. You don't have to have as much energy to get out. And so then, even at the low temperature, we've got a much higher fraction of molecules that have enough energy to escape. So if the intermolecular forces are weaker, evaporation will happen faster.
What if you mix something that has a higher evaporation rate with, like let's say you mix alcohol with water, would that make water evaporate faster, or only alcohol still evaporate?
If you mix a volatile liquid such as alcohol and a non-volatile liquid such as water, it will reduce, I believe it will reduce the rate of evaporation of both.
Okay.
Because now there's competition at the surface area. Yeah, there's a bunch of factors in that, because you also have strength of intermolecular forces. If you're disrupting the intermolecular forces by mixing those two liquids, then that could cause the evaporation to increase.
So whichever of those two is stronger, the reducing
Yeah.
or increasing?
Yeah, I think it could go either way. But in general, I think it would reduce the rate of evaporation. It's a good question. So evaporation, we were talking about. Condensation is the opposite. That's where we have a gas condensing into a liquid. So they're opposites. And we have a point at which the rate of evaporation and the rate of condensation become equal. And that is called a dynamic equilibrium. And that's why we jumped ahead to chapter 15, because there's little bits and pieces in these next chapters that make so much more sense now that we understand what equilibrium is. So when we have a closed container, we have evaporation and we have condensation, and those will at some point come to an equilibrium where the rates are equal. And then we have a gas above the liquid, and that's going to exert a pressure, and that's called the vapor pressure. So the vapor pressure of a liquid is the partial pressure of its vapor when it's in dynamic equilibrium with the liquid. Yes, a picture. So let's say we put some water into an Erlenmeyer flask and we stopper it. Initially, there's essentially no water in the gas state above here, but as soon as we put the water in here, some of the water molecules begin to evaporate. So right now we have a significant rate of evaporation. We have no condensation going on because there's nothing up here to condense yet. So we go along and more water molecules evaporate, and now some of them have had time to zing around a couple times and crash back into the water. They crash back in, they get trapped, that's condensation. So now the rate of condensation is increasing. The rate of evaporation is staying fairly constant. The surface area is the same, the temperature is the same, the strength of the intermolecular forces are the same. So the rate of evaporation is fairly constant, but now the rate of condensation is increasing. We let this continue, and eventually the rate of condensation and evaporation will become equal, and we have dynamic equilibrium. We have water molecules leaving the liquid and going into the gas state. We have other molecules coming from the gas state and entering the liquid state. So we have water vapor, water in the gas state, that exerts a pressure. And it's measurable, and it's called the vapor pressure. And so that's what we were subtracting off when we collected our gas over water in lab. Because you not only have the gas that you're interested in, but you also have this water vapor.
Partial pressure?
It's the partial pressure. Yeah, so vapor pressure is partial pressure. Okay, but not all partial pressures are vapor pressures, right? There's a reason there are two different words. The vapor pressure is when that gas is in equilibrium with its liquid. If there's no liquid present, then it's simply called a partial pressure. So this is when there's liquid present. So that vapor pressure is going to depend on the temperature. Because what happens when you increase the temperature? What happens to the rate of evaporation?
Increases?
It increases. So the rate of evaporation will increase. And so then the rate of condensation will also increase, but you're still going to end up with more gas molecules than you did before. And so the vapor pressure goes up.
And the equilibrium shifts to being less liquid and more gas?
Yes. The higher the temperature, the farther the equilibrium shifts to the gas. The strength of intermolecular forces will also affect the vapor pressure. If the intermolecular forces are weak, then you'll have more gas present than if the intermolecular forces are strong, because it's easier for the molecules to escape. So the vapor pressure depends on temperature and intermolecular forces. It is not dependent on the surface area. Rate of evaporation depends on surface area, but the vapor pressure doesn't. Because if you increase the surface area, you increase the rate of evaporation and the rate of condensation. And so that doesn't shift the equilibrium in either direction. So vapor pressure depends on temperature and intermolecular forces. So when you're dealing with a single substance like water, its intermolecular forces are always the same. And so that's why we can look up the vapor pressure in a table. It is only dependent on temperature. So boiling. Boiling is related to evaporation, but it's a little different. So we've all seen water boil, right? You get all these bubbles forming and it's a rolling boil, and now it's time to put the spaghetti in, right? So the boiling point is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure above it. As we increase the temperature of a liquid, its vapor pressure will increase because the rate of evaporation is faster and faster and faster. The vapor pressure increases when it gets to the point where the vapor pressure equals the atmospheric pressure. The water boils, the liquid boils. So the thermal energy is enough to cause water molecules in the interior of the liquid to become gases as well. And so that's why we get these gas bubbles forming in here. They have enough kinetic energy to go into the gas state even in the interior of the liquid and not just at the surface anymore.
Question.
Yes?
When you use electricity to do the same exact thing, does that technically mean it's boiling because those particles have enough energy, or are they just simply turning into gas?
When you mean use electricity, do you mean pass electricity through the water? That's a different process. That's actually a chemical reaction because you're decomposing the water into hydrogen and oxygen gas.
Oh, that's right.
Yeah, so that's a little different. Boiling is just a state change. It's a physical change. So the molecules themselves are not changed, just their interaction with each other. It's a good question. I'll just talk about this now instead of paging through slides and coming back. So the boiling point of water depends on the atmospheric pressure. If we go up into the mountains, if you go to Denver, Colorado, where they're a mile high, which is about, actually, Kings Canyon, I think, is a mile high too, isn't it? 5,280 is a mile. So you go up to Kings Canyon, National Park, and water boils at a different temperature up there because the atmospheric pressure is lower. You heat the water up, but now the atmospheric pressure is lower, and so at a lower temperature, you get to the point where the vapor pressure is equal to the atmospheric pressure. And I don't know if you've ever noticed this on cooking instructions for baking and various things. It'll give high altitude instructions. It does that because things happen at different temperatures.
Is the same principle apply to a pressure cooker?
The same principle applies to a pressure cooker. A pressure cooker does the opposite. By increasing the pressure, the water will boil at a higher temperature, and so you can cook your food faster. We'll get to the heating curves and we'll understand why that makes a difference.
Okay.
So we have heating curves, and I think we'll see a picture in just a minute. So imagine you're heating a pot of water, the temperature is rising, When it starts to boil, the temperature stops rising, and it stays at that temperature until all the water has boiled away.
It was reduced to a temperature substantially higher.
Yeah, once the water boils away, once the liquid boils away, the temperature shoots up.
But if I have a container filled with water and I introduce it to temperatures exceeding like 1,500 degrees, so the water would only boil obviously faster, but the water itself would never exceed a higher temperature.
Right. The water will not go to a higher temperature until all of it has turned into the gas state.
That's cool.
It's crazy when you think about it.
Yeah.
So anytime you have a mixture of boiling water and steam, the temperature is going to be 100 degrees at 1 atmosphere of pressure. So that pot of spaghetti, or the pot of water that you're going to put the spaghetti in, if it just started boiling, or if it's been boiling for 5 minutes, because you're putting a lot more than 100 degrees Celsius of heat at the bottom of that, it's going to be the same temperature. If it's boiling, it's 100 degrees. Doesn't matter how long it's been doing that. It just stays
Is
there.
that how superheating works? Like when you have pure water and then you put something in it, it explodes into gas instantly? Or,
We can talk about superheating water later.
okay.
That's happened in my microwave and it blew the door open. Didn't blow it off, but it blew it open. So here's a heating curve. So this is looking at what happens during boiling. So we're starting here around room temperature, and you add heat and the temperature increases linearly until you get to the boiling point. And then it's flat. And the temperature doesn't go up until all the water has been converted to the gas state, and then the temperature goes up.
Is that second curve a little more steep?
It is, yeah. The slopes, we'll learn that the slopes of these lines are significant. So let's think about what's happening when water evaporates. Which molecules are leaving? The higher energy molecules or the lower energy molecules? The higher energy molecules. So if you have higher energy molecules leaving, what does that do to the average kinetic energy of the liquid?
Brings it down.
It brings it down. So you're adding heat, because you've got this pot on the stove, you're adding heat, but all the higher energy molecules are leaving. And so that's one way to think about how does the temperature stay the same. You think about, in the summer when it's so stinking hot here and you sweat, right? And a breeze comes and you're like, oh, it feels so good, because your sweat is evaporating. Why does that cool you?
Takes heat away.
Because the higher energy molecules are leaving. And so what's left is a lower temperature. That's how a swamp cooler works, by taking the higher energy molecules out. It lowers the temperature of what's left. So evaporation is an endothermic process. It takes heat in to convert something from a liquid to a gas. And when we think of boiling water, that makes sense, that it's an endothermic process. So our sweat evaporates, and it takes heat from our bodies and gives a cooling effect. Now, in a high humidity situation, like in a sauna or in Minnesota or Georgia, the air is already pretty full of water, and there's just not really much room. So relative humidity is the percentage of water that's possible. So like the day my husband and I got married, it was 95 degrees and 95% humidity in Ames, Iowa. I mean, it was just steamy. It was nasty.
Things are melting.
Things are just, yeah, you melt into a puddle and you sweat and it doesn't do any good. It doesn't evaporate. And so you tell your body, would you just quit it already? This isn't helping. Your body says, yeah, but I'm hot. This is the only thing I know how to do. We lived in North Carolina for a while. The same thing there. And you take a shower in the morning and you walk 2 blocks to the bus stop and you stand there in the shade. And you're sweating, just waiting for the bus. And you think, why did I take a shower? Well, so that you could have fresh sweat on you instead of old sweat, I guess. But high humidity means that the water doesn't evaporate as well because there's a lot of condensation also occurring. So if evaporation is endothermic, then condensation must be exothermic. And that one's like, what? Kind of hard to think about. Condensation is exothermic. When a gas condenses into a liquid, it releases heat. That's weird, huh? Well, what happens if you hold your hand over steam, a steaming pot of water?
Condensation.
It gets really hot, doesn't it? That heat is from the energetic gas particles now. When they condense into liquid, they're slowing way down. Where did the energy go? Into your hand. Steam can burn you. Okay, steam can burn you much more efficiently than water. It's very dangerous. Pardon me? Air conditioners work by compressing gas and expanding gas. And one process is endothermic and one process is exothermic. And so that's why it needs to vent to the outside, because what it's really doing is you're separating heat. So you're moving heat from one thing to another, and you want the hot part to go outside. That's why if you run if you're hot and your air conditioner's busted, and you open the door to the refrigerator and you just stand in front of it, okay, well, yeah, you're feeling the cool air coming out, but you can't just leave your refrigerator and freezer open and expect it to cool your house. Because in the process of cooling off the inside, it's actually going to generate more heat on the outside. And so the net effect will be that your house will be warmer than before. It has to vent to the outside. So since condensation is exothermic and evaporation is endothermic, water in the air moderates temperature. Here in the valley where our relative humidity is very low, we've had days recently where the temperature swung 40 degrees. We had a low of 40 at night and a high of 80 during the day. Just crazy temperature swings. And we're all used to that. You all are used to that. I did not grow up here. And so I've gotten used to it because I've lived here for 16 years now, but it still just blows me away sometimes, because in Minnesota and Iowa, where it's more humid, where I grew up, the temperature in the summer when it's humid might vary only by 10 degrees. 85 during the day, 75 at night. It just doesn't really cool off because the air is so full of water that it doesn't change temperature very well. And the same thing happens, there's always a week or two in the summer where it just doesn't cool down at night, right? And it's kind of muggy. We say, ooh, it feels muggy, because there's more water in the air. And that moderates the temperature and doesn't allow it to cool down. The sun goes down and we expect it to get cool, and it doesn't, because there's all of this water.
Question.
Yes?
I don't know if it's related directly to gas and pressure, but why does hot water freeze faster than cold water?
That's a good question.
Because it has more kinetic energy.
That actually is I don't fully understand that one myself, but I will tell you that the last time I was in Minnesota for Christmas, the high was 12 degrees below zero, and the low was 26 degrees below zero. And we had heard about this, and so we actually ventured outside and did this. We boiled a pot of water. We took a boiling pot of water outside. We threw it into the air, and it was frozen by the time it hit the ground. If you do that with room temperature water, it doesn't happen. And it has to do, there's some sort of a momentum. There's some sort of a momentum in that change that causes it, if it's the temperature difference is greater, that it happens faster than if the temperature difference is less. It's kind of crazy. It's not a catalyst. I really don't understand it.
Okay.
I think it's a little more physics than chemistry.
I was wondering, well, perhaps is it because of the amount of energy that is already placed in the water that the molecules have actually become so active that when it's thrown into a temperature that is, like even when you threw it in the air and it's separated at larger space, that energy is already mechanically moving. The energy is going to be blown off faster rather than having a more solidified structure that's going to retain its energy.
It's possible. If somebody will send me a text message to remind me, I will look it up. Or you guys could look it up and tell us about it on later. You can look it up right now, I don't care. But yeah, that is a thing that happens. The other cool thing about this, okay, so in the valley, maybe you guys down here where there aren't as many citrus trees aren't so aware of this, but up in Reedley where citrus is a big deal, in the winter the temperature falls and it gets down around 30 degrees and the farmers get nervous. And what do? They water their fields. They spray water. They make sure the water's ground. There's running water all over the place. Well, how does that keep the citrus from freezing?
Because the more energy is being added, and it doesn't have as much activation energy, it takes longer to freeze.
It does. It takes longer to freeze. What happens is that as the water condenses, it's an exothermic process, and it releases energy. And so the temperature cannot drop below 0 degrees Celsius, 32 degrees Fahrenheit, until that has all condensed. And so the more water you have in the atmosphere, the longer it will take for that temperature to fall. And so what they're doing is they're stalling. Okay, and a lot of times it's just a couple of degrees difference. It's not going to, you can't just heat the world by pouring water all over the place. But you can keep the temperature from, I think they have to go down to like 26 degrees for a certain period of time to damage the oranges. And so if they can just keep it up a little bit higher for a little bit longer till the sun comes up, then they're okay. And so they can stall it out that way. But it's because when water condenses, it's exothermic and it actually gives off energy. It's kind of crazy to think about. But we have more citrus fruit because of it. Okay, heat of vaporization. So here we get into a little bit of math. Heat of vaporization, the symbol is delta H, VAP. So that kind of makes sense, H for heat, VAP for vaporization. That is the amount of heat required to vaporize 1 mole of a liquid. So to take 1 mole of a liquid and turn it into a gas. That requires energy. That's an endothermic process. And so we quantify that as how much energy to do that to 1 mole of a liquid. So if we look at water, the heat of vaporization of water at its normal boiling point is 40.7 kilojoules per mole. So for 1 mole of water, it's going to take 40.7 kilojoules of energy to vaporize that. So the chemical equation is pretty simple. H2O liquid going to H2O gas. Delta H for that process is 40.7 kilojoules. And just like when we talked about heats of reaction, this was for the molar amounts in the equation. So this is for 1 mole of water. So this is 40.7 kilojoules for 1 mole of water. And that is at 100 degrees Celsius. Because it will only, well, just because. So the delta H is positive because we have to put energy in. It's an endothermic reaction. If we do the opposite process, if we go from a gas to a liquid, now the energy change is the same, but it's in the opposite direction. So if we write this reaction backwards, H2O gas going to H2O liquid, we have the same number here, but we have a negative sign, because that much energy is being released, is leaving the reaction. So delta H is negative. It's an exothermic process. We can use the heat of vaporization to calculate how much energy is needed to vaporize a given amount of liquid. So the heat of vaporization ends up being a conversion factor. So here's a handy table. There's my arrow, there it is. Heats of vaporization of several liquids. And these are given at the boiling points and at 25 degrees Celsius. Because the amount of energy needed to vaporize it will depend somewhat on the temperature. So for water, oops, sorry, pointing at the wrong place. Water's 40.7, isopropyl alcohol 39.9, acetone 29.1, diethyl ether 26.5. So 26.5, that's less energy to vaporize. What does that tell us about the strength of the intermolecular forces? Does diethyl ether have weaker intermolecular forces or stronger? It takes less energy to convert it into a gas. So they're weaker. Mm-hmm. So we can do calculations. Oh joy. Some of you like that. Others of you don't. That's okay. And we're jumping in here with kind of a complicated one. So let's read the whole question. A drop of water weighing 0.48 grams condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature of the metal block? And it says the specific heat capacity of aluminum is 0.903.
We have to convert the Kelvin and then move it back to Celsius in the end? Or?
No, actually we don't. It really feels like there's some things missing from the lecture. Well, we'll fill them in as we go along. Oh, I know. Never mind. Okay. Just thinking quietly to myself. Okay, so let's think about this. Sometimes it's helpful to draw a picture, because if you look at this, it's probably not immediately obvious what you should do with all these numbers. So we have a block of metal, and that's 55 grams, and that's aluminum. And then we have a droplet of water. Actually, let's make that blue. So we have a droplet of water that's 0.48 grams, and that's water. So the water is condensing onto that surface. The block of the block of aluminum was originally at 25 degrees Celsius. 25 degrees Celsius. So when water condenses, that's an exothermic process, right? Heat is released. And it's saying, well, what if all that heat went into the block of metal? What would the temperature of the metal be? So we've got two things going on here. We've got the water condensing and releasing energy, and then we've got the block of metal absorbing that. So let's treat them separately. So how much heat is that, is the water going to release? We have 48 grams of water. We were just talking about heat of vaporization. The heat of vaporization is the amount of energy per mole that is required to evaporate or the amount of energy per mole that is released when something condenses.
100 degrees Celsius.
So we would need to use the one that's at 25 degrees Celsius,
Oh,
which I don't want to lose all my scribbles, so I'm going to have to go look it up in the book. Because 40.7 was the one at 100, but that's not the one we want to use. 44? Thank you. So 44, that's kilojoules, I believe, per mole. But we've got a mass of water. Do grams cancel moles? No. Could we convert grams to moles? Sure we can. So we want grams on the bottom and moles on the top, so that moles here will cancel out and grams here will cancel out. Now, if you're thinking ahead, you might convert to moles first and then multiply, but you can do it in any order. The relationship between grams and moles is the molar mass, and for water, that's 18.02 for 1 mole. So that gives us 0.48 times 44 divided by 18.02. So that should probably have 2 significant figures. I'm going to give it 3 because we're not really done yet. 1.17, and that would be kilojoules of energy. So the water is releasing 1.17 kilojoules of energy. That energy is going into the block of metal. So this is going back several chapters. Do you remember MC delta T? Q equals MC delta T. Looks like kind of like MCAT. The amount of energy equals the mass of something times the specific heat capacity times the change in temperature. So here what we just calculated is Q. This equals Q. This is the amount of energy released by the water condensing that's going into the metal. We're given the mass of the metal, its initial temperature, and its specific heat capacity, so we can calculate the final temperature. So let's solve this for delta T. We'll we'll divide by M and C. So delta T equals Q over MC. And we just figured out that Q was 1.17 kilojoules. The mass was 55 grams. Okay, there was no zero on that. 55 grams. And the specific heat capacity is 0.903 joules per gram degrees Celsius. So the grams cancel out. Did joules and kilojoules cancel out? No. Well, there's a couple of ways we could get around this. Since I don't have a lot of space, what I'm going to do is I'm just going to cross out kilojoules. Kilo means 1,000. So that is 10 to the third joules. Okay? Now they cancel. And we have 1 over degrees Celsius, and so that is degrees Celsius. So the change in temperature is equal to 1.17 times 10 to the third divided by 55 divided by 0.903, and so the change in temperature is 23.6 degrees Celsius. Delta T equals the final temperature minus the initial temperature, the difference. So if the initial temperature was 25, then the final temperature is 25 plus 23.6. So 48.6, or we would round that to 49. 49 degrees Celsius. So that's a good place to stop. That is what I would consider a fairly complicated problem. You have two different processes. Any questions? There's different ways to deal with those units not aligning. You can convert them separately, or you can convert them all at once. Yes?
So you add 25 degrees Celsius to 23.6?
Right. But let's move it up here. So 23.6 equals T final minus T initial. So to move the 25, I have to add it. Yeah. It's not always immediately obvious, that one. Any other questions? I'll see you in lab.